Hello everyone, welcome back to Exploring Quantum Physics. I'm Charles Clark, and in this part we're going to look at the impossibility of classical mechanics as a framework for describing magnetism of any sort at all. It's really quite a striking discovery made in the earlier part of the 20th century, and this will lead us to start to solve some actual problems of magnetism using quantum theory.
So let's start by looking at how one thinks about the properties of the magnetic properties of materials using classical mechanics. So the sort of culminating research result in this subject is described in this paper, which you can find on additional materials. I have the original there. It's in French, but many of you will be able to read the equations. A remarkable result found by Hendrika van Leeuwen, who showed that classical statistical mechanics couldn't describe the magnetic properties that are possessed by every known material system. And it's not like it gave a description which was off by a factor of 2 from what it really is. It basically says the phenomenon of magnetism is impossible. Well, this is quite a blow to classical physics. Now, it came, in 1921, so by that time it was quite clear from atomic spectra, for example, that classical mechanics had to be supplemented. But this is a result that affects a phenomenon that used to navigate ships, used throughout industry. Magnetism, very important fundamental feature of the world. So why is there a problem in classical mechanics? Here's a mnemonic device for remembering why such a result might exist. It's the Lorentz equation for the motion of a classical charged particle. And so you see the acceleration is perpendicular to the velocity. So the acceleration r dot dot is proportional r dot cross b. So this means that r dot dot r dot dot is equal to 0. So do you see that the Lorentz equation implies that the kinetic energy of the system is constant? It's independent of the field. So if you have a system, particle in some state of motion, you turn a magnetic field on and off, you're not going to couple energy into the system. So actually we derived this in the previous section. Basically, the energy looks rather like just the classical kinetic energy when you use the velocity rather than the momentum. Now, to take this a bit further, this page and the next one sort of outline the essence of van Leeuwen's proof. The arguments are actually quite straightforward once you have the underlying architecture in place. And so now this deals with sort of the foundational element of classical statistical mechanics, the so-called partition function. So for those of you who haven't had a course in statistical mechanics, I apologize. Just try to do the best to follow. This is a very standard procedure. If you have, this is a partition function for one particle which is governed by a classical Hamiltonian, which is just the same entity that we have in quantum mechanics, except that p is now a classical variable. And you integrate, you weight that, and the particle's at a certain temperature. So you divide the energy, the Hamiltonian function, by the thermal energy, which is Boltzmann's constant k times the temperature. You exponentiate the negative value of that and integrate over all position space and all momentum space, then divide by h cubed. So this is therefore a pure number, and its interpretation is the number of thermally accessible states for the system. So this represents the size of the volume of phase space that can be occupied by a particle that's subject to random temperature fluctuations. Now, why one does this is because all of the properties of a system at finite temperature are described by taking the derivative of the partition function with respect to various quantities. So the derivative with respect to electric field gives the electrical susceptibility. The derivative with respect to the magnetic field, the same thing, compressibility, and a lot of the basic response functions of a material system can be gotten from the partition function and its various derivatives. Okay, so here's the first point, that when you look at this and you take the usual version of the Hamiltonian, then do you see the partition function can be factored into two parts. And look at this. The first factor is dependent upon the spatial configuration of the potential. But once again, like in the contribution to the arguments in the virial theorem, the integral over the momentum is a universal one. It doesn't depend on the details of the potential. And what do you know? It's again one of these Gaussian integrals. So you've invested so much time in figuring out the natural and efficient way of solving this. I'm going to give you yet another opportunity to try it. Congratulations on getting that Gaussian integral right. I know that you all enjoy them every bit as much as I do. I do love Gaussian integrals. I mean, they're so useful. But now there's something that requires perhaps a little bit more thought. So how do we introduce a magnetic field into the problem? Well, the answer is by the approach that was outlined in the first part of this lecture, the minimal substitution. So wherever the momentum occurs in the Hamiltonian, you insert a shifted momentum, and the momentum is shifted by a vector quantity, which is the vector potential associated with the field. Okay, now I say that you should be able to evaluate this as well. Why don't you pause and think about that? By evaluate it, what I mean to say is I think you should be able to see what happens in this integral without doing a lengthy and specific calculation. And here is the result. It is obtained very easily by just defining a new variable. Let's call it pi equal p minus q over ca. Then you see that just shifts the origin, and so the origin of this object is displaced in space, but you're integrating over all space. So the integral is independent of the vector potential. Now, in some sense, that does make a certain amount of intuitive sense because, as you may recall, we said, well, the integral, the vector potential has this ambiguity. It's undefined up to a very general function, which is a gradient of something. So that's, you might say, this is a feature that it's independent of a of x, but it's also a bug because it means that no account of the magnetic field appears when you take a a real material system well described by thermodynamics and turn on a magnetic field. Nothing happens. So, what's the resolution of this? Quantum mechanics changes this in a very fundamental way, just like it changes lots of things in a fundamental way, but in this case it's a macroscopic phenomenon which everyone is deeply familiar with. And it does so through this commutation relationship. So when you see something like this, two things commute and give an imaginary number, this should remind you, for example, of the commutation between position and momentum, which is IH bar. This looks like that, and we're going to make the correspondence more clear. And just ahead of time, let me say that in classical mechanics, you can make Hamiltonian vanish by just taking V equal to 0. But in quantum mechanics, because you have the V's are now non-commuting operators, you can't simultaneously fix the values of all of them. So this This quantization condition plus this form of the Hamiltonian gives, this commutation relation plus this form of the Hamiltonian sort of guarantees the lower bound on the energy due to the uncertainty principle, as we'll see in a moment. This was first explained by Landau at the age of 22, quite remarkably, in 1930, and this is a reference to the original paper in German. So we're now going to solve the Schrödinger equation for a charged particle in a uniform magnetic field, very important. And I've sort of given you hints as to how the solution should go. There's a number of steps, and I'll walk you through it. So our start is with these two foundational conditions. So the first step is to choose the axis the axis of the magnetic field. So the magnetic field is constant, so it's in some direction. So we just use that direction to define the third axis, or the z-axis you might call it. It doesn't matter which one we choose, but that leads immediately, you choose one such axis, so I've chose the third, and then that means that V3 commutes with V1 and V2. Now how do you see that? Well, you see, if you have a 3 here, then the other one has to be a 1 or a 2. If you have a 1 here, then you would have a B2. Well, but B2 is 0, and similarly. So in other words, V3 commutes with V1 and V2. And so that also means it commutes with the Hamiltonian, so it provides a constant of motion, and we'll deal with that one a little bit later. And now, for the third step, we know we have this only one commutation relationship that has the consequences of which have to be understood. And I've chosen this compact form of representing it, where this omega is the cyclotron frequency. That's the orbital frequency of a classical charged particle in the magnetic field. Okay, and as I mentioned before, whenever you see something like this, think back to the fundamental commutation relationship of quantum mechanics, which is kind of responsible for everything. You know, the harmonic oscillator quantization comes from this. So we can now define a linear combination of the V's. So here's this A, and then A dagger would be the same thing times V1 minus I V2, because the V's are Hermitian. And when you do this, you find that you get this commutation relation. You might want to pause and just verify that that comes from this, because you'll see it as it'll enlarge your understanding of how quantization emerges just from commutation relation. However, I'm pretty much filled up the page here. There's about 2 steps left, so I'm going to move the important parts of this onto the next page. So here we have the quantization condition, the commutation relation, the Hamiltonian. Then here are these definitional matters, and the construction of the raising and lowering operators. So this is the raising and lowering characteristic commutator raising and lowering operator. And so, in fact, the fact that you have this says you've got a harmonic oscillator. Guaranteed. So now, how do the A's relate to the Hamiltonian? That's the final step. Well, we just take A dagger A, simply given here, and now you can see you get a V1 squared plus V2 squared, which just come from the 2 exterior terms, and then there's another contribution from the commutator V1, V2, and that gives this piece here. So then, I mean, obviously this term here is just proportional to the Hamiltonian. So we do the simple math, and what you see is the Hamiltonian is now the Hamiltonian of a one-dimensional harmonic oscillator of frequency omega. And then there's an additional term, the free motion, mv3 squared, free motion parallel to the field, and a quantized oscillation perpendicular to the field. Now, you know in classical mechanics that the charged particle undergoes a circular orbit in the plane perpendicular to the field. So it's, you say it's intrinsically a two-dimensional motion, but this, the commutation relationship here gives a one-dimensional harmonic oscillator spectrum. This is a problem worth studying in more detail if you like quantum mechanics a lot. The choice of a specific gauge and then solving the Schrödinger equation is in differential equation form is most instructive, and you'll learn quite a bit about the phenomenon of gauge invariance. But you see, we managed to get the spectrum here without any invocation of a particular gauge. We only used the field, and it was only the field that appeared in the fundamental commutation relationship that's responsible for this quantized oscillation. So what we've done here is reproduced Landau's description of diamagnetism. That's one aspect of magnetism. It's a repulsive force. So Landau showed that because of this quantization, this is the minimum energy that a particle can have in a It's a 0 point. There's a 0 point energy of motion in a particle in a magnetic field that's proportional to the field. And so, in other words, if you have an ensemble of such particles and then you increase the magnetic field, their energy goes up. So they feel a repulsive force due to a magnetic field. In fact, all materials feel a repulsive force, but in some cases the attractive forces of magnetic forces are much stronger. This repulsive force is sufficient to do magnetic levitation at room temperature. There's a link in additional materials to a little video I made of levitation of a chip of pyrolytic graphite by a simple 4-magnet trap. This is made possible because pyrolytic graphite, for some reason, has an extremely high diamagnetic susceptibility. Now, the more important aspect of magnetism, the one that's responsible for actual magnets and for most of their applications, has a different origin. It's also due to properties of electrons, but it's tied up with their spin. And so that's the next subject on our list to study during this lecture.